Hey guys, welcome back to another video. In today's video, I'm going to be talking about related rates, so let's begin. Related rates are an extension to implicit differentiation, but it comes with real-world applications. Related rates involve variables that change over time, such as height, volume, area, and length. Writing an equation that relates those variables, like volume is like pi over 3 r squared times h, or area is 4 pi r squared, something like that. It also involves implicit differentiation that helps find the related rates. It also involves plugging in known variables and solving for the unknown rate or value. So let's start with some examples. So a circle's radius increases at 3 centimeters per second. We're going to find how fast the area increases when r is equal to 5. So let's write the derivative dr with respect to time, the derivative of the radius, or the rate of change of the radius with respect to t, is equal to 3 centimeters per second. We're trying to find how fast the area increases, increases when r is equal to 5. So we know that area is just pi r squared, because we have a circle and the area of a circle is pi r squared. So what we can do is we can implicitly differentiate. So we can say that the derivative of a with respect to time is equal to 2 pi r multiplied by dr dt. So we're trying to find how fast the area increases, so this is what we're looking for over here. And we just need to plug in r and dr dt. So it's just 2 pi multiplied by 5 multiplied by 3. So we have 15 times 2, which is equal to 30 pi centimeters squared per second as our answer. Okay, so for this one, we have a ladder that is 10 feet long and is leaning against the wall. So let's say this is 10 feet, and we're saying that the bottom slides away at a rate of 2 feet per second. We're trying to find how fast is the top sliding down. So let's say the top is height. So we're trying to find the rate of change of the height when the bottom is 6 feet away from the wall. So say b is equal to 6. So what we can do here is use the Pythagorean theorem. So we can say that the height is based on 100, which is the hypotenuse, minus b squared is equal to height squared, but we can use the square root to just say that it's this. So we're trying to find dh dt. So what we can do is say that h is equal to 100 minus b squared to the power of 1/2. If we implicitly differentiate, we get that dh with respect to t. Derivative of h with respect to t is equal to 1/2 times 100 minus b squared to the power of negative 1/2 multiplied by negative 2b. So we'll get that the rate of change of the height is equal to negative b, because the negative 2 and the 2 cancels out, over 100 minus b squared 1/2 multiplied by the rate of change of the base. I forgot to include that rate of change of the base, because although we have b, we still have to put the derivative of b because we're implicitly differentiating. So you have negative b over 100 minus b squared to the power of 1/2 multiplied by the rate of change of the base. So if we plug in values, we say that the change whenever base is equal to 6, so negative 6, 100 minus 36 is 64. So we're going to take the square root of that, which is 8. So we have negative 6 over 8. So multiplied by the derivative of the base with respect to time. So you have negative 6 over 8 multiplied by 2. So you have negative 12 over 8. Or if we divide by 4 in common factors, we have negative 2 over 3. So we can say that the rate of change of the height is negative 2 over 3 feet per second. Okay, so now you're being told that water is being poured into an upside down cone at 10 centimeters cubed per second. and that the cone's height is 12 centimeters, the radius is 6 centimeters, and we're trying to find the rate of change of the water's height when the water is 4 centimeters deep. So let's draw this out. We have the cone, we have this. We say that the rate of change of the volume is equal to 10 centimeters cubed per second. We say that the height is equal to 12 centimeters and that the radius is 6 centimeters. So we know that h is equal to 12 centimeters and that r is equal to 6 centimeters. And we're trying to find dh dt when h equals 4. So what we can start off with is the volume of a cone, which would be equal to pi r squared multiplied by h divided by 3. So we know the derivative of volume, but we don't know the derivative of r. So what we're going to do is solve for r in terms of h. As you can see over here, h is twice as big as r. So you can say that r is 1/2 of h. And since we have an r squared here, we can say that r squared is equal to h squared over 4. So we have that volume is equal to pi h squared over 12 multiplied by h, or pi h cubed over 12. So when we differentiate, I'm going to erase, no, I can't erase. I'm going to differentiate right now. So dv dt is equal to, so we're going to multiply by 3 because that's the power rule. So we have 3 over 12, so that's going to be pi h squared over 4 multiplied by dh dt. So now we have what we're looking for, dh dt, but we need to solve for it in terms of the other variables. So I'm going to clear everything here. So we have dv over dt is equal to pi h squared over 4 multiplied by dh dt. And what we're going to do is just cross multiply dh dt, and we're going to plug the values in. We know that the rate of change of the volume is going to be equal to 10 multiplied by 4 over pi. H is 12, so 144, and that's equal to the rate of change. So once we simplify this, we can get this is equal to, sorry, I plugged in the wrong value for h because it's asking for when h is 4 centimeters. So this should actually be 16 over here. Okay, so to reiterate, we're at here. We have 10 times 4 over pi. H squared is 4 squared, so you have 16. 4 over 16 is 1 over 4, so we have 4 pi. 10 over 4 pi is equal to dh dt. And once we simplify, we get that the rate of change of the height is equal to 5 over 2 pi centimeters per second. Okay, so now we are being told that a street light 15 feet high lights a person who is 6 feet tall and that is walking away at a rate of 5 feet per second. So let's say that their rate of change of x is equal to 5 feet per second, where x is the distance of how far away they are from the pole, and s is the length of the person's shadow. We're trying to find how fast the length of the shadow is moving when x is equal to 10 feet. So let's begin. So what we're gonna do here is analyze that there's two triangles. We have a triangle right here and another triangle right here. These two triangles share the same theta. So this theta is equal to this theta, and they also share this 90 degrees. So we can relate these two triangles by using tangent of theta. So tangent of theta for the big triangle is 15 over x plus s, and tangent theta for the tiny triangle is equal to 6 over s. But these two are going to be the same. So what we can do is solve for s, because we're trying to see the rate of change of s with respect to time. So we're going to have to solve for s. So what we can do is multiply by s. 15s is equal to 6x plus 6s. Subtract 6s, so you have 9s is equal to 6x. Divide both sides by 9. So you have s is equal to 2 over 3x. We differentiate. We have ds over dx is equal to 2 over 3 dx dt. this should be dt, sorry. So this is just 2 over 3 multiplied by 5, which is 10 over 3 feet per second. So the shadow is moving, the length of the shadow, S, is moving at a rate of 10 feet per second. Okay, so for our last problem, we have that a balloon is rising at 10 meters per second at a point that is 100 meters away horizontally from an observer. Let h be the balloon's height and theta be the angle of elevation from the observer to the balloon. Find the change of angle with respect to time when h is equal to 60 meters. So we're going to start off with the balloon. So let's say that there's a right triangle and that this distance is 100 meters, and then we have some angle over here, and we're trying to find it when the height is at 60 meters. So it stays right here, and the rate of change of the height is equal to 10 meters per second, but we're trying to find the rate of change of the angle. So what we're given is the opposite and the adjacent. So what we're going to do is use tangent theta to relate the height with the adjacent. So whenever you do related rates, usually you don't plug in values first. You usually differentiate first and then you plug in the values, because if you plug in values first, you're going to get a completely wrong answer. So we're going to keep h as h here and not going to plug in 60 for now. So this is h over 100. So what we're going to do is differentiate both sides. So we have secant squared theta, because that's the derivative of tangent, multiplied by the derivative of theta with respect to time is equal to 1 over 100 derivative of height with respect to time over 100. So we need to find what the value of secant squared theta is. So we know that secant squared theta is equal to the Pythagorean identity of 1 plus tangent squared theta, because this comes from sine squared theta plus cosine squared theta is equal to 1. When you divide everything by cosine, you get tangent, 1, and secant. So we just need to find what tangent squared theta is. So tangent theta is h over 100. So if we were to square that, we just get h squared over 10,000. So we're going to get 3,600 over 10,000. This cancels out. Now we have 36 over 100, which is 18 over 50, 9 over 25. And since we're looking for secant squared theta, we're going to add a 1 to it. So it's going to be 9 plus 25, which is roughly 34. I accidentally erased everything. So this is essentially where we were at. I just moved the secant over here because we just want the change in data on its own. So we're going to plug in values into here. So you have 1 over 100 multiplied by the rate of change, which is 10. So these cancel out. So now it's just 1 over 10 multiplied by 1 over 34 over 25, which is roughly 1.36. Well, it should be 1.36. So what we're going to get is 5 over 68 radians per second. And that is our final answer. This is the end of the video. Thank you for watching, and stay tuned for more.